Hello, my students. This is a brief walkthrough for the introduction to Chapter 7 for us. In this chapter, we will remind ourselves where we left off with the atom in Chapter 2, and that was with the Rutherford model. We will then look at the increased experimentation and understanding of light, which led to the Bohr model of the atom. We need to understand how atoms are made to release light, and then how Bohr used the line spectrum data to create his model of the atom. We need to understand, whenever we say that light has a dual nature, what that means, and what were the experiments and the conclusions that were drawn from those experiments to make that conclusion. And then, of course, how does seeing light as having a dual nature lead us to the quantum model of the atom? Then, do we understand the workings and truly what the quantum model conveys to us? How exactly is the electron perceived? And how is that different, ultimately, from Bohr, Rutherford, Thomson, Dalton, all the way back to Democritus? We also will remind ourselves of the basic setup of the periodic table, the periodicity of the periodic table, the periodic families, and so on. So this is a really good, meaty chapter. What we need first is to remind ourselves of the electromagnetic spectrum. So please, take a look, do some Googling. You need to minimally know at least 5 of the different types. We don't need to know the wavelengths or frequencies by heart, but we need to know how they relate to each other. For example, radio waves have longer wavelengths, thereby lower frequencies, thereby lower energies. We also need to be reminded of the wave equations. C is lambda nu because we assume that all electromagnetic radiation travels at the speed of light. Electromagnetic radiation is anything that travels with a wave-like nature. It has an electric component and a magnetic component. Now, we're going to see where this equation comes from. E equals h nu. Nu is frequency, lambda is wavelength, c the speed of light, E energy in joules, h Planck's constant, and nu. We need to be able to solve anything within these equations. Please read in your book about the historical way that we differentiated between matter and energy. We saw matter, of course, as anything that has mass and volume. Energy, no mass and no volume. You can actually pinpoint where matter is. You cannot exactly pinpoint where energy is. So traditionally, matter was seen as a totally separate thing from energy. Please look at the black body experiment. So please research it, take a look, and make sure that you understand where Max Planck developed this equation. Also make sure you look at the photoelectric effect and what Einstein and Planck concluded about photons. Their conclusion about light directly conflicted with what Thomas Young showed us with diffraction. Make sure that you look up the double slit experiment and that you understand the workings and how that was used to conclude that light or electromagnetic radiation is only wavelength, not matter-like. Here's where we interject about Niels Bohr. Please review how we can make atoms release light. Please review the line spectrum and how Niels Bohr utilized the line spectrum of elements to create his model of the atom. Make sure you understand how his model differs from the Rutherford model. He also utilized experimental evidence and developed what we call the Bohr equation. Make sure that you know the limitations of the Bohr model. They are nicely conveyed to you within your textbook. Well, the Bohr equation really is utilized most often to answered these kinds of things. What exactly is the energy? Now, we use today energy level. He used, of course, orbit. What is the difference in energy between the orbits? And then if we know that, we can calculate the wavelength of the energy given off, or the associated frequency, corresponding then to the line spectrum. I have these problems for you. If you would like, you can pause to look at my work for these. Make sure that you can solve these and that you understand my work. Here is just a summary of what you need to be able to do after this first lesson once you've researched on your own. Here's just a representation of the Bohr model of the atom. And here's just a nice diagram of the photoelectric effect. I want to show you some other graphics that I found in a different textbook, which I think are very, very nice. Here is just a nice showing to us of the different properties or measurements we can make about waves. Wavelength, and then the relationship of wavelength and frequency. Here's where amplitude comes in. I think this is just another nice presentation of the electromagnetic spectrum, and we see what a very, very small portion we can detect with the eye. Also, make sure that you understand that Roy G. blue-violet is inverted as far as longer wavelength, shorter wavelength. So actually violet has shortest wavelength, highest frequency, highest energy. Of course, the different wavelengths of light, different frequencies, different energies, allow them to be separated when placed through a prism. Here is an example of utilizing C equals lambda nu. Here is a really nice this kind of graphic presentation of the conflict of viewing light as a particle versus a wave. A very nice graphic of the double slit experiment. Here's E equals lambda nu. Make sure that we understand how the word quantum is used. Planck was the first to communicate that electrons are quantized. And here's an example of utilizing the two equations, C equals lambda nu and E equals h nu, together to be able to solve as one instead of two steps. So that's another different version that can be presented to us. So we will pick up with lesson 2 with chapter 7.